continuing with frequentist research, I want you to go back to a video entitled Standardized Variables and take another look. It's very short. It's an add-on in the section about descriptive statistics. Sort of a O-and video. To get accustomed to this, go back and look at it, then come back here. Okay, you're back. 1, 2, 3. This is a standardized variable, a z-score. All I'm doing over here, I did it in the video, just referenced with the age variable that had an odd distribution because of a 50-year-old in the mix. We're talking about it here with respect to the x variable in question, which is a test score that we assume all 13,000 Ole Miss students took, and we have a sample, a random critically sample of 10. So you can standardize xi by taking out its mean and dividing by its standard deviation. And if you need to go back again under descriptive statistics to find how you calculate the standard deviation. Now that you've done that, you're all familiar with standardizing variables, and you know the purpose. It's to make, no matter what they were, make them into normally distributed variables. And so we'll think about now, once more, repetitive sampling of drawing samples first of 10 over and over and over and over again, randomly, from the pool of 13,000 Ole Miss students, we'll call our population, and treating the x bars as individual observations again. So they're going to be different. It'll be different, especially with 10. It'll be very different every time we draw a sample. Each time, we're going to have the x bars now in a column of data, just like this, and subtract from them their mean, which we know, because x bar comes from a random pool, we know it's unbiased, and we know its mean is mu x, the mean of the population. So we're going to subtract each x bar subtract the mean of the population from each x bar and divide by the standard deviation of x from the population, the 13,000, to create this little z-score of x bars. This is really, really a fundamental result in statistics and in mathematics. The central limit theorem. The central limit theorem tells us that this quantity, or you can look at it that way, tells us that this thing is normally distributed. And importantly, it's not just normally distributed, so we'll do this. I'm going to call that little squiggly means is, capital N, normally distributed, with, moreover, mean equal to the population mean, and variance critically equal to the population variance divided by, this is critical, the sample size. In our case, this is 10. In our case, this is 10, but the critical thing to note here is that the variance shrinks as the sample size goes up. So I'm going to erase some of this and draw a picture, right? Keep going. Pay no heed for now to these axes. Pay heed to this one. So I'm just saying that the quantity that you have now in your notes, the z-score of, you can think of it as the z-scores associated with the x bars collected through sampling that goes distributed normally. And the variance really relates to how close it comes to ux. The x bars are distributed normally about the population mean, and the variance, sigma squared, divided by the sample size. We're going to restate this as a sort of standard deviation on top, and I'm going to call it a standard error of x is equal to sigma over n this is important. We know, you don't know calculus. Some of you don't know calculus. Many of you don't know calculus. Other people know calculus, and you can find the area underneath this curve. And the area underneath this curve is going to depend critically on the size of the sample. We start with a sample of 10, and we gather another one, and another one, and another one, and another one. They fall very, very predictably. There's one standard error out from the mean, and here's the second one. One standard error out from the mean, here's the second one. 2 standard deviations out from either side of the mean leaves us area under the curve. Leaves us area under the curve about equal to 95%. I say about equal, not because we don't know, because if the numbers are really large, we know exactly. I say about equal because I went 2 standard deviations this way, 2 standard deviations this way, and the official number is 1.96. Don't care that you know the official number, do care that you know the rule of thumb. 2 standard deviations in the normal, no matter, this is a normal curve, no matter how steep, no matter how flat, 2 standard deviations this way from the mean and 2 standard deviations that way leaves 95%, approximately 95% of the area, and gives us the tools to conduct frequentist inference by building what Bayesians hate more than anything in the world, which is a confidence interval. I'm going to do it right here. So now we're going to look at this scale. Here's 0, 50, 77, and 100. It's bounded by 100. You're going to find something fairly clever here on purpose about, and it's going to tell you a lot about having really, really, really small samples. What I want to build here is an interval within which 95% of the x bars of n equal 10 will fall. Say that one more time. I'm going to build an interval within which 95% of the x bars from n equal 10 will fall. I'm doing repeated sampling, something that never happens in reality. Well, actually, happens in reality all the time. On a computer, we'll simulate this. You will see these pictures and generate them yourself using R to get a better feel for it, but not until you've learned it in this way. So 95% confidence interval, we know that about approximately 2 standard deviations in both standard errors in both ways. How do we, so here's the standard error again. We don't have the standard deviation from the population. So instead of using this, we're going to estimate it, and we estimate it using, guess what? The standard deviation from the data. So now this is we put a hat on him because he's now an estimate. By the way, that's always supposed to be the square root of n. So it's the variance over n, and so if you take the exponent down to 1, it turns into the standard deviation of x over the square root of n, which is very important. Now here's the mean, here's x bars. Over here I have statistics. That's our standard deviation, 17, right? And we have everything that we need here to build a 95% confidence interval. And so we're going to do it. It's going to look like this. I have an observed mean of 77, and I want to come 2 standard errors this way. And I'm estimating my standard error with, can you hold?